Good morning, honors chemistry students. Today, I would like to review the first of 4 polyatomic ions that I would like you to examine on the backside of your molecular geometry lab. But before we do that, I want you to think about the following scenario. Today, I'd like to actually examine the structure of the hydronium ion. And so to do so, I would like you to consider what happens when 2 water molecules that are liquid collide to form a hydronium ion, which is an ion which has a +1 charge, and we consider it to be aqueous, which means that it is present in solution. And along with that, the other ion that forms is a hydroxide ion, which is also considered to be aqueous. It's important to note that both the hydronium and hydroxide ions could collide and reform the water molecules as well. To get a better representation of what's going on chemically, what I'd like to do this is to examine that reaction in the electron dot format. Keep in mind that this double arrow means that this is an equilibrium reaction, which means that water molecules can collide to form the hydronium and hydroxide ions, which are charged species, and those charged ions can also collide to reform the water molecules. What I would like you to consider is, suppose we had a water molecule like such that was colliding with a neighboring water molecule, and I'm going to represent those water molecules with Lewis structures. Remember, or be reminded of the fact that the electrons in these bonds get pulled closer to the oxygen atom, so it's slightly negative, and the hydrogen atoms are slightly positive. And the same could be true of the other molecule that I've represented here, in which the oxygen is slightly double negative. Let me make certain these are longer to look like charges rather than dots. And the hydrogens are slightly positive because there's an asymmetric pull of the electrons involved in these bonds. Since the oxygens have greater electronegativity, the electrons that are involved in the bonds with hydrogen are pulled closer to the oxygen, which makes the oxygen slightly negatively charged and the hydrogen slightly positively charged. When those similarly charged molecules come in close proximity to one another, it's possible for this highly electronegative oxygen to pick off this hydrogen, which has very low electron density because its electron has been pulled closer to the oxygen atom and its own water molecule. And so in doing so, you come up with a structure that looks something like this, whereby both of the electrons in the bond with hydrogen are supplied by the central atom of this water molecule. And as such, it's picking up a proton, which then basically confers a charge of +1 on that ion because it has one more proton than electrons. And likewise, the other water molecule, and you know what I may do here, I think it would be instructive, would be to use X's for the electron dots here rather than dots, so we can trace which valence electrons are assigned to which atom. It's clear that the species that remains would be what we call a hydroxide ion. And notice that when this water molecule was picked off by this oxygen, that what's left behind are the valence electrons of that oxygen. And so since this water molecule is now missing a proton, it has an overall charge of -1. And it's important to use those brackets because the charge is thought to exist over the entire structure of the polyatomic ion. If you're curious about why those charges are the way they are, one needs to think about how many protons you have in this molecular system. You have 8 for oxygen, 1 for each of the 3 hydrogens, so this system would have 11 protons. And then we need to think in terms of how many electrons there are. Oxygen would have 8, each hydrogen would have 1, so 8 and 1 is 10. The difference between those would then be +1. So that's why we say that the hydronium ion has a charge of +1. And likewise, with the hydroxide ion here, it's clear to see that oxygen has 8 protons, hydrogen has 1 for a total of 9. However, in this case, this valence electron is left behind from this hydrogen. So thus, it's clear to see that we have 1 additional electron because we have 8 for oxygen, 1 for this hydrogen is 9, and this hydrogen would be 10. So therefore, when you account for those, that particular species has a charge of -1. And in fact, I think it might even be helpful to represent this particular electron with a different symbol, so we know that it came from the proton that was donated to this water molecule. So suffice it to say, this particular ion is known as the hydronium ion, and this particular ion is known as the hydroxide anion or hydroxide ion. So our goal today is to represent the hydronium ion in our representation for the molecular geometry lab. So that being said, we're going to have to work with a little bit of short space. The first column of the 19 columns that you need to represent is that for H3O plus 1. That's the symbol in charge for hydronium. The second column is the illustration, which we generally reserve for doing once you've done the paperwork, once you've done the modeling, you represent your model there on the illustration. And then the next column is for the AELD, or the atomic energy level diagram. It's clear with 1 oxygen atom and 3 hydrogens that oxygen is going to be the central atom, and oxygen has 8 protons and 8 neutrons because its atomic number is 8, which means we need to represent 8 electrons. So we have 2 electrons on the first energy level, and then we have 6 more to represent, 2 in the 2s, 1 in this 2p, 1 in that 2p, 1 here, that's 1, 2, 3, 4, 5, 6, correct? So there's our central oxygen atom for hydronium. And then we need to represent 3 hydrogens. So we're going to place 1 hydrogen here with its 1 proton, no neutrons, and 1 valence electron. We're going to represent another hydrogen here with its 1 proton, no neutrons, and 1 electron. And then the question becomes, where do we represent the next hydrogen atom? And it would be using both these pairs of electrons, which are donated from the central atom to a proton. All that's being transferred to this molecule is a proton with 1 positive charge and no neutrons, and it's going to take advantage of the fact that that hydronium ion already has an oxygen atom that has a lone pair of electrons to donate to a proton. And to represent this properly, we're going to say that the hydronium ion has a charge of +1, okay? Because it's a system which has 11 protons once again and 10 electrons, so the overall charge is +1. All right, so that being said, the next diagram we're going to represent is the orbital notation diagram. We're going to have to really watch our space here. So in terms of orbital notation, we're going to start with a central oxygen atom, which has 2s and 2p electrons. The 2s electrons, it's got 1, 2, 3, 4, 5, 6. And you can clearly see that we have places to form pure covalent bonds with or polar covalent bonds with the 2 hydrogen atoms, one of which could be represented here. Okay, another one could be represented here. And so we're going to have one bond here. And one bond here. And then we need to represent one more bond between oxygen and hydrogen. And notice how this is going to be. We're going to have another hydrogen here, but notice this is missing an electron. And so both the electrons in this bond are going to be donated from oxygen. And I should point out that such a bond as this bond is referred to as a coordinate covalent bond. Coordinate covalent bonds are covalent bonds in which the electrons involved in the bond come from the central atom, okay? Or are donated by the central atom. The next diagram that we're going to represent is the electron dot diagram. And the electron dot here has oxygen as a central atom. I tell you what.
Teachers and students, pardon this interruption. We have a couple of bus changes and an announcement.
That oxygen has 6 valence electrons.
9229.
We're going to place one hydrogen here,
We'll be riding
another hydrogen there,
bus 9002
and
will be
the
riding
hydrogen
bus
with the coordinate
9007.
covalent bond here.
Again, bus 9002 will be riding bus 9007. And for those students who are participating in track and field, your practice today will be at 2:45.
And once again, this is going to have an overall charge of +1.
Participating in track and field,
and then we're going to go on to our structural formula.
Thank you and have a great weekend.
Wasn't that beautiful to give the same announcement over and over on a different day? All right, so once again, this oxygen has 6 valence electrons. Each hydrogen has 1, except for this hydrogen, both the electrons come from the central atom of oxygen. So with respect to a structural formula, it would look something like this. And in this structural formula, we're going to use an arrow pointing towards the oxygen to show that this bond is actually a coordinate covalent bond. We need to prepare ourselves for the school bell that's going to ring or the chime that's coming up. And so once we get to the structural formula, then we can start looking at electrons in the system and electrons needed for stability. So let's look at electrons in the system. How many electrons do we have in this system? Well, it looks like oxygen has 6, and then you have 1 for each hydrogen. That's a total of 8 valence electrons. So we have a total of 8 valence electrons in the system. And interestingly enough, to be stable, oxygen needs 8. Each of the hydrogens need 2. So 8 and 2 is 10, and 2 more is 12, and 2 more is 14. So we'd say there's a total of 14 electrons that are needed for stability. And in terms of calculating, I'll just do this here, the number of bonds that would be predicted for this molecule. You'd look at the difference between, whoops, now I did it, 14 and 8. This should be a 14 and 8. Divided by 2 electrons for bond. That's a difference of 6 electrons divided by 2 electrons for bond per bond, which would predict 3 bonds. By the way, this numerator 6 actually represents the number of electrons involved in covalent bonding, which would be 1, 2, 3 pairs, or 2, 4, 6 total electrons. So we would predict for this molecule that there should be 3 bonds with the molecule. So we're going to move from that to the Lewis dot structure. I'm going to try to conserve on space here because we're going to need to do that. So I'm going to look at the Lewis dot representation. We're going to have oxygen as our central atom, and we're going to have 3 bonded pairs here, here, and here. Keep in mind that this is your coordinate covalent bond, and the Lewis dot also represents the lone pairs of valence electrons that are on a central atom or even not on a central atom. So our Lewis dot structure is going to look like that, bracketed with a charge of +1. The next consideration we have is to calculate bond type. We calculate bond type to get an idea of whether or not each of these bonds is polar, but we should already have an inkling of that, because if we look at the electronegativity of oxygen, which is 3.45, and compare that to the electronegativity of hydrogen, which is 2.20, that difference looks to be 1.25, which would make that bond actually a polar covalent bond, okay? Which means each of these bonds are polar. However, since we know the overall molecule is charged, we're not going to represent the separation of charge between the central atom and the hydrogens. The next calculation that we need to do is to examine the total pairs of electrons around a central atom to predict the arrangement of those electron pairs. And for oxygen in this molecule, we know we already have 3 bonded pairs and 1 lone pair for a total pair calculation of 4. So we're predicting that there should be 4 total pairs of electrons. Vesper theory does make a prediction for 4 total pairs of electrons, stating that they repel themselves to positions that minimize the repulsion between them. So we would have, in terms of Vesper theory for this molecule, we'd have an oxygen atom, which has three hydrogens bonded to it, and we might look at the fact that one of these is a coordinate covalent bond, and then we are going to have to represent a lone pair. Vesper theory would predict that this bond angle is 109.5, and we would predict that this structure is tetrahedral, and we would close this off with a bracketed molecule with a charge of +1. So that's our Vesper theory structure, and a companion theory to Vesper theory is hybridization. Hopefully we've got enough room to squeeze this in, which seeks to explain the arrangement of electron pairs around a central atom that are bonded to other atoms. So we're going to say that 4 total pairs predicts sp3 hybridization, which predicts that we would have 4 hybridized sp3 orbitals that are degenerate, meaning they're equivalent. One of these is going to be behind the paper. We're going to have a lone pair here. We're going to have a bonded pair with hydrogen here, a bonded pair with hydrogen here, and a bonded pair with hydrogen here. So there's our 3 bonded pairs and 1 lone pair. And the bond angle that's predicted is 109.5 degrees. And the arrangement of those electron pairs is predicted to be tetrahedral. And the hybridization scheme is predicted to be sp3. And again, we're going to bracket this molecule with a charge of +1. So that's our hybridization scheme. The actual geometry is somewhat interesting, however, because I'm going to come back over here. When we look at the actual geometry, we only take into account bonded pairs, not lone pairs. Are you with me? So we have 3 bonded pairs and 1 lone pair. So the way this would look is we'd have an oxygen, we'd have 3 bonded pairs, and we'd have a lone pair, but we're going to draw it close to that oxygen because we do not use lone pairs to predict geometry. And the presence of this lone pair has the net effect of repelling these bonded pairs and squeezing that bond angle down from 109.5 to roughly 107 degrees. And the predicted geometry is referred to as trigonal pyramidal. Or for short, we just refer to it as pyramidal. And we box this off with brackets with an overall +1 charge. So that's our actual geometry for the hydronium ion. It's similar to ammonia in that it's sp3, but because of the presence of the lone pair, instead of the predicted geometry being tetrahedral, it's actually trigonal pyramidal, which differs from trigonal planar in that these hydrogen atoms are arranged as the base of a pyramid. The next 2 columns would be bond energy, which we would actually have to look up, but you shouldn't have to look that far. And keep in mind that bond energy is in kilojoules per mole. You can actually think of this in terms of you've got 3 bonds that are the same bonds that are present in the water molecule. So you can get your bond energy values and bond length values from water. And for me, I have a bond energy that I've noted of 464 kilojoules per mole. So the bond energy here is 464, and the bond length, which is generally given in picometers, is around 90. I want to double check this. My eyes are failing me. Is around 96 picometers. All right. And then the next column is going to be our AXE system. Here we have a central atom that has 3 bonded pairs with 1 lone pair. So we'd say our central atom is oxygen and represent it with an A. You have 3 bonded pairs, AX3E, because it's got 1 lone pair. AX3E molecules are pyramidal. And in terms of polarity, we are going to just jump out there on a limb and say that this molecule is polar because of the fact that it is charged, right? It's charged, so therefore in an aqueous environment, it behaves as if it's a polar molecule. So the next molecule we're actually going to look at in the next video is going to be the hydronium ion. and we'll come back with that next.